The Ohm's law says states that at constant temperature, at constant write down today's date, Ohm's law, at constant temperature, at constant temperature, the potential across a circuit, at constant temperature, potential across a circuit is directly proportional to the current flowing through the circuit. Is directly proportional to the current flowing through the circuit. So we have V proportional to I, or V is equal to IR, or V upon I is always a constant and is called R. Simply resistance. Simply resistance. Okay. So V upon I is equal to R. V upon I is equal to R. And this is called as Ohm's law. This is called as Ohm's law. Formula for Ohm's law. But this happens only at constant temperature. When the temperature is constant, only then Ohm's law is applicable. Otherwise, it is not applicable. Now, what is the value of R? R represents resistance. R represents resistance. And it is defined as the obstruction in the path of the flow of electric current. Resistance is defined as the obstruction in the path of flow of electric current. Okay. So R is the resistance. It is defined as the obstruction in the path of flow of electric current. R stands for resistance, and its value means it is defined as the obstruction in the path of the flow of electric current. Now, from where does the obstruction comes? Now you know that the current flows, when the current flows, it is because of the charge. The current flows, that is because of the charge. Okay. The current that is flowing is because of the charge. Okay. Now when the current is because of the charge, then what happens? That when the current is because of the flow of the charge, current I is flowing because of Q. Q means charge, right? So this charge, the current is because of the when there's a wire, and in this what happens? Electrons flow. The electrons are flowing, and when electrons are flowing, the material medium, the molecules, they are offering resistance in the path of the flow of this current. Okay, so who is offering resistance here? Who is offering resistance? The molecules of the material, they are offering the resistance. Okay, so the material medium, its molecules are offering the resistance, right? So its molecules are offering the resistance. So molecules of what? Material medium are offering the resistance, right? Now this obstruction or the resistance is created by the material medium, and it depends on the resistance of a wire depends on directly the length of the conductor. Means more the length, the more is the resistance. Less length, less resistance. So it depends on The resistance depends on the length of the conductor. And second thing is that resistance depends on inversely proportional to the cross-sectional area. Means that the cross-sectional area through which the current is passing is thick. The cross-sectional area of the wire through which the current is passing is very thick. Then the resistance will be less. And if wire is very thin, then resistance will be more. Okay. So resistance depends on two factors. The first one is the length of the conductor. Second is inversely proportional to the cross-sectional area. If you combine both of them, then R proportional to L by A. And if you keep a constant here, then R is equal to rho times L by A. Okay, R is equal to rho times L by A. Where rho is called specific resistance. Where rho is called specific resistance. Okay. Note note down all this in your fair notebook. Okay, write down where this is the symbol. This symbol is called as rho. Okay, the symbol is called as rho. Write down where rho is called specific resistance. Where rho is called specific resistance and is defined as the resistance offered by a conductor and is defined as the resistance offered by a conductor whose length is 1 meter, whose length is 1 meter and cross-sectional area 1 meter square, whose length is 1 meter and cross-sectional area is 1 meter square. So the resistance depends on number one, the length of the conductor. Resistance is directly proportional to the length of the conductor. The resistance of a wire is inversely proportional to the cross-sectional area of the conductor. Combining both of them, we have R is equal to rho times L by A, where L is the length and A is the cross-sectional area. Rho is called a specific resistance. So if suppose length is equal to 1 meter and cross-sectional area is also 1 meter square. So R is equal to rho times 1 upon 1, 1 meter upon 1 meter square. So that will give you what R is will be equal to rho. Hence, the resistance of a conductor whose length is 1 meter and cross-sectional area 1 meter square is called the specific resistance of the conductor. The specific resistance of a conductor only depends on the specific resistance of a conductor depends on which factors? Do you know? It depends, number one, specific resistance of a conductor depends on only the nature of the material. It neither depends on length, it neither depends on cross-sectional area. It depends on the nature of the material. So rho is specific resistance or resistivity is depends on the nature of the material of which the wire is made. Okay, clear? Next you see resistance is in series in series and resistance in parallel. A series combination is like this way. This is the resistance combination in series. So let us consider three different resistances R1, R2 and R3. They are connected with a battery in series. This is R1, this is R2, this is R3, and this is the battery here, positive terminal of the battery and the negative terminal of the battery. So you are being asked to calculate what is the resistance in series. So you see when the current passes here, the same amount of current has to pass through the resistance 1, resistance 2, resistance 3, right? Same current passes through all the three resistances and finally it comes back to the battery. So you see, write down, In series combination, in series combination, write down in series combination, current remains same. In series combination, current remains same. In series combination, current remains same. Whereas in series combination, current remains same. Whereas potential distributes. Potential distributes. In series combination, current remains same, whereas potential distributes. Means when the same current has to pass through the wire here, so the all the current has to pass through resistance 1, through resistance 2, through resistance 3, and finally it comes back to this terminal length. So the same amount of current is flowing through all the three resistances R1, R2, and R3. So you see R is equal to R1 plus R2 plus R3. This will be the formula here. How? Let's obtain that formula. Write down. Let the potential across R1 is V1, R2 is V2, and R3 is V3. Right? Let the potential across R1 is V1, and R2 is V2, and R3 is V3. Therefore, potential V is equal to V1 plus V2 plus V3. Therefore, V is equal to V1 plus V2 plus V3. That's okay. The potential distributes. So whatever V is the potential of the battery, so that same potential will be what? That will be distributed. So it will go to some potential will be across V1, some across V2, and some across V3. So V is the potential of the battery. So V is equal to V1 plus V2 plus V3. This point is clear. If V is the potential of the battery, then the potential V will be distributed, and some potential will go to V1, some will go to V2, and some will go to V3. So V is equal to V1 plus V2 plus V3. Okay. Now V is equal to what? According to Ohm's law, V is equal to what? IR. V is equal to IR. According to Ohm's law, V is equal to IR. So here you write here what? IR. V1 is equal to IR1. V2 is equal to IR2, and V3 is equal to IR3. You see everywhere the current is same, because all the I have already given you that the current here remains same, but the potential distributes. If the current is remaining same, that means I is same, and V is distributing. So the V is equal to V1 plus V2 plus V3. V means what? Potential according to Ohm's law, V is equal to IR. V1 is equal to what? IR1, and V2 is equal to IR2, IR3. Now dividing whole equation by I. Dividing whole equation by I, divided by I. So you get what? R is equal to R1 plus R2 plus R3. This is called as, this is the combination formula of the resistance in series. This is the combination formula for resistance in series and its derivation. You can see here, this is a circuit. Three resistances are there. R1 is there, R2 is there, R3 is there, and the potential across R1 is V1, across V2, V2 across R2, and V3 across R3. V is the potential of the battery. So here in series combination, the current remains same, but the potential distributes. So V is equal to V1 plus V2 plus V3. And so you see V means IR1, IR according to Ohm's law. V1 IR1, V2 IR2, V3 IR3. Divide whole equation by I, so you get R is equal to R1 plus R2 plus R3. So this means that in series combination, the resistance offered will be equal to R1 plus R2 plus R3. Got it?